This is panel 3, water recycling, reduction, reuse, and recovery. 4 reasons to be here. Begin with RE reasons. Come on, that's as good as I can do. Yeah, thank you. I'm here all week. Our first speaker today is Christopher Drover of CTO. He's the CTO of ZwitterCo. And he's going to talk about fouling-resistant spiral wound elements for treating difficult streams, including fish oil. Membrane can handle chlorine, which is not allowed with conventional RO membranes. And so this is really quite along the same lines as the themes we've been talking about for some of these other things. And fouling resistance is a big thing that keeps coming up again. So, Christopher?
Sure.
You can use that one if you want. You can stand here. That was the live mic. And this is the clicker.
Excellent. All right. Well, thanks, everybody. As Mr. Truby said, I'm Chris Drover. I'm the CTO and one of the co-founders of ZwitterCo. So we have been spending the last couple of years trying to bring to market a new, what we call exceptionally fouling resistant membrane chemistry. And so what we mean by that, there we go. This is a membrane chemistry that uses a new type of polymer to form the selective barrier. And we like to think that it enables filtration that's not possible with other membrane chemistries. And so we're really focused on expanding the market for membranes and going after applications where traditionally filtration or membranes in particular haven't been possible. A little bit about us. We're based right outside Boston, Mass. in Woburn. We've been have met products in the market for about 18 months commercially. We've sold 15 projects in that time. And we did just do a capital raise earlier this year. And so we've been expanding quite a bit. And we're excited to enter some new markets and introduce some new products next year also. So the way that we see it, we're very focused on industrial wastewater and industrial wastewater reuse in particular. As we see the problem, about 1 out of every 6 gallons of freshwater withdrawal ends up as industrial or agricultural wastewater. And that if we can get to a future where industry is able to reuse more and more of their wastewater on site, we see a future where you limit competition of industrial processes with public water supply as resources get strained. Industry can secure access to the water they need for their future growth and not be limited by availability of water for their business. And probably most interestingly, to take what would be harmful waste, isolate valuable byproducts from that, and potentially be able to valorize some of that waste. This is a challenge today because a lot of these wastewaters, particularly from food and food adjacent spaces, really high in fats, oils, proteins, and traditionally these have been a big challenge when we look at membrane separations and filtration. So I've got a little bit of the technology here. So what we've basically found through all the pilot testing we've done and the plants that we have operational is that our membranes are really not susceptible to the permanent irreversible fouling that you might see with a high fat, oil, and grease stream. You can kind of see what this looks like. This is a time lapse of a 30-minute water rinse. Obviously, some of this is material impacted into the spacers. But what we found is that having a really high fouling resistant sheet goes a long way toward mitigating the long-term buildup of material, even in the spacers of the spiral wound membrane. What we do to achieve this is we take Zwitter ions, as you might imagine from our name. This is a really hydrophilic chemistry. It's actually quite challenging to make functional membranes out of it because it likes to dissolve in water. But we use some techniques that use some self-assembling polymer architectures. And we're able to form a selective barrier, like you see in the little image here, that's composed of small channels of Zwitter ionic material embedded in a structural matrix. Because the pores, the channels themselves, are made out of this chemistry, that makes those pores really, really resistant to oil absorption and permanent fouling. And this lets us do things with these membranes that you traditionally don't think of being able to do. So what we aim to do, the opportunity that we see, obviously recover clean water, avoid discharge, and capturing these co-products, which is a common theme we see in a lot of the projects we've done. That can be everything from nitrogen-rich fertilizer, protein-rich animal feed. We've seen a couple of projects that we've worked on where there's a sale of that concentrate once the material's been removed from water. And we want to, we're looking to do that in some of these areas you see here, the cartoons. We've got poultry projects running right now, bioprocessing, fermentation. And this year we've started to engage with some of the seafood industry, which is why, we sort of got interested in BlueTech Week. And I'll go through a little bit in a moment here what that looks like. So seafood processing is a pretty challenging from a wastewater standpoint. In addition to producing a high BOD and fat, oil, and grease load in the wastewater, you think about the maritime environment in a port. Real estate is not inexpensive. You've got odor concerns from traditional wastewater operations. And most significantly, it's really seasonal, right? So as different, shrimp comes into season, a fish comes into season, a traditional wastewater plant really struggles to adapt to these huge swings in flow and the water chemistry. So, our sort of proposition is that as new membranes come to market, including obviously the ones that we are offering, there's some other paths that are opening up and other ways we might think about wastewater management in the seafood industry. We did a trial earlier this year as we started to engage here. This is from a shrimp peeling operation, so highly seasonal. The difference between the average flow and the peak flow is a factor of 6, so very challenging to design a wastewater plant for this. The membrane that we have out on the market today can do complete suspended solids removal, near complete or complete fat, oil, and grease removal, depending on the sort of analytical method you use, as well as a majority of the biochemical oxygen demand. And as I mentioned before, they clean up very nicely, even after a few weeks of processing. So here we've got the untreated seafood shrimp peeling wastewater, the permeate, and the concentrate, which is only about 2% of the volume in this case. So that kind of brings us to where to go from here. We see a couple different scenarios that can make sense in seafood processing. Water reuse is perhaps one of the more tantalizing, where we'd be able to reuse some of this spent water, perhaps with additional processing to meet whatever standards are needed and go back into that process. There's also opportunities for byproduct recovery, so nitrogen-rich and phosphorus-rich liquid wastes under the right conditions, if they're kept free of chemical contamination, can be quite valuable in the fertilizer market, and get some minimal or zero discharge from these operations into the maritime environment. We see that in seafood processing. We're also interested in aquaculture, and in addition, some non-food applications like bilge water and other wastewater operations from ports. So more than anything, I'd say you tell us. We're here to meet with folks from this space and learn more about what we might do for wastewater management with new tools. So with that, I will turn it over.
Thank you, Chris. We're going to do questions at the end, but I'll ask you one right here while I've got you. How about ballast water? Different from bilge water.
Have a look at it.
Okay.
I would love to. So please reach out.
Okay. It's one that I keep getting asked about, and I'm not sure if there's any there, but there's a lot of regulation there, that's for sure. Our next speaker is Mr. Jayesh Shah. He's the Senior Global Marketing and Product Manager with NITO. He's located in Oceanside, California, at the hydronautics facility. They have 14 beautiful acres there in Oceanside and have been there for a long time. Hydronautics is one of the biggest employers in Oceanside. They're a very big company, and they are one of the dominant membrane suppliers. It's reverse osmosis, ultrafiltration, that sort of thing, globally. Jayesh interfaces globally with commercial and government offices, educate and inform about the beneficial use of membranes in a variety of water applications. And if you were here this morning, you heard him asking questions along with his associate Shannon. So now we get to hear what Jayesh has to say, and we'll ask him some questions.
So first of all, I think thank you, TMA, for the opportunity. And Randy, Gil, Eric have already set the tone for what we are trying to discuss today. But I'm just going to have more stuff which would be providing more education if possible. So I think if you look at some inputs from the World Economic Forum, the biggest crisis, which we all kind of know, but the slide kind of talks about it all, is the global water crisis. And there are aspects as to what is kind of leading us to this stand. But there are different solutions which are existing and upcoming, which can help us fight this. So very quickly, if you look at, there was a question in the morning, but if you look at the Earth, I think at this point of time, everybody knows this, 71% of the Earth's surface is covered by water. But only 2.5 to 3% of this water is available as fresh water, which you can kind of use in different applications in terms of surface water, groundwater, and also water which is in glaciers and ice caps. But the third aspect is that you just have 0.7% of your water available on this planet Earth, which can be accessible, right? Either for your surface water requirement, drinking, cooling, bathing. And these are some of the highlights as to where the water are actively being used. We know about the domestic and public supply, very important for human life. But also beyond that, the food industry, which is more of the agriculture and irrigation, which kind of uses 37% of water. And then industrial is the big behemoth, right, where a lot of developments are happening. So that's where a lot of water is being used. And also power generation worldwide. Looking at the slide, this kind of speaks about that 87% of the water presently used in US is kind of used in the three industries: power, it could be nuclear, thermoelectric, gas-fired, irrigation, and industrial. But when I speak of industrial, we are also speaking of mining, livestock, and aquaculture, which Christopher was kind of alluding to. And just for the information of the audience here, I think most of the people know, but what is wastewater? Obviously, you have these different segments that we spoke of: domestic, which is municipal wastewater, irrigation, industrial, and thermoelectric, and all of them consume water in different form, different condition aspects, but all of them also get transitioned to what we call wastewater or dirty water, right? So the biggest focus here is to kind of take care of this. Now, just trying to deep dive, if we speak of municipal water, seems very easy, municipal and industrial, but let's try to understand the different constituents or composition of the water, because that's where the challenge is, that how do you kind of employ the right process, the right membrane to be able to treat this. So when you speak of municipal water, obviously you have a lot of human waste which comes out in the sewage, food scraps, oil, soaps, chemicals, different type of detergents, bacteria and viruses, and all of this have different effect, including the charge that they have. Industrial water is, again, very varied because it depends upon the type of industry you're talking of. If you're talking of textiles or pharmaceuticals or food and beverage, the composition would vary a lot, but you would definitely have oils, heavy metals, pesticides, chemical solvents, other than the total dissolved solids. And in California, I think at this point of time, 900 wastewater treatment plants deal with 4 billion gallons of wastewater produced each day. That's a big number, and which is growing because we need more growth to kind of treat the wastewater. Some aspect of global wastewater issues and challenges. So 80% of the world's wastewater at this point of time flows back into the ecosystem without being treated or reused. Now, that could be because of the vacuum of technology and process, but the awareness is coming in. Just going back to a different part of the world, in China kind of on an annual basis discharges around about 75 billion tons of wastewater. That's more than the annual flow of the Yangtze River, which is the Yellow River, right? So a lot of wastage of the wastewater there. India kind of discharges an estimated 500 million gallons per day of industrial wastewater into one of their biggest river, which is the Ganga River. And of the 44 trillion gallons of wastewater collected, which we kind of discussed in the earlier slide, only 2% of water is at this point of time treated and reused. So you can understand there's a big scope where we could have more water from the wastewater. And by as soon as 2025, it's estimated that half of the world's population will be under extreme water scarcity. And this is a fact that everyone would agree to. So let's just try to understand on a higher level what are some of the solutions to combat water scarcity. And people speak about wastewater treatment. And what we like to emphasize are the 4 R's, which are reclaim, recycle, reuse. And one of the other R's that was also added by Eric in the morning is recover. So you are in a position at this point of time to reclaim, recycle, and reuse the water. And what that does for us, that it kind of provides water for different irrigation and industrial purpose. It conserves the fresh water, which you typically want to use for drinking water, can generate sustainable source of water, but especially with the zero liquid discharge, which Gil spoke about in the morning. And one buzzword that everyone kind of speaks of, but they do not know because it's very intangible, is how can it support your ESG initiatives and also help you reduce your carbon footprint, right? Because that's very important. So when we speak of water conservation, we kind of spoke about two aspects. Gil kind of emphasized that MLD and ZLD. So let's just try to understand what does this stand for. So when you speak of MLD, it stands for minimum liquid discharge, where you kind of have the wastewater, you treat the wastewater through specialty products or specialty membranes, and you would have limited liquid waste, right? So what you're doing is kind of reducing the waste, and you're in a position to kind of reclaim and reuse it. And the second aspect is what we call zero liquid discharge, where you would kind of treat the same wastewater, but you would have no liquid waste, right? And it's not magic. You are probably coming down to a stage where you're reducing the water volume, the wastewater volume, to the lowest level possible with the highest concentration. And then you have thermal equipments which can kind of convert this into salts. And as Eric spoke about in the morning, and Eric, thanks for all the pricing aspects, you can understand the value of the different salts that can be mined from this waste. And I'll just speak about this, but these are some of the key objectives: that you have lowered waste volumes, which is very, very important, so that you're not disposing a lot of wastewater, recycling water on site, and this kind of has got a direct impact on your acquisition cost, right? Because if you're not treating your wastewater, you're probably acquiring water from some sources, and also kind of helps you to meet the different environmental discharge standards available worldwide and regionally. Also helps you improve the environmental performance all around. But very important, and this is something that people are kind of discovering and many companies are moving towards it, that it can also help you in many cases recover valuable resources. So as Eric mentioned, and I completely agree with it, if people start emphasizing and focusing on this, there will be a time where the water that they treat would be free of charge because they are mining their valuable from the salt, right? And this is where people say that you see waste, but we see profits. So just kind of trying to jump into the MLD part, you start off with a freshwater source, and then you kind of condition the water as per your industrial requirements. So this goes into different industries, also the municipal segment. And then as I spoke, everything gets transitioned to wastewater. So you will have a lot of generation of wastewater. And at this point of time, there exists a lot of treatment processes whereby you can employ membrane processes, in most of the cases, specialty membrane processes, so that you can treat the water, and then you could achieve two aspects. One is you can reduce your waste if that's your requirement, if you want to kind of dispose it off based on the environmental norms, or you could also kind of treat it further and recycle and reuse as fresh water. This could go back to the utilities or any of the plant requirement of the process, but depends on what the requirement is. The second part is that you could take that extra step by looking at further specialty membranes, which can help you with further concentration. But the difference between MLD and ZLD is that you do need to have a downstream thermal equipment, which is kind of taking care of your, low volume waste, but converting that into salt. So this is the same loop where you start with fresh water for different applications, generating into wastewater. And this point of time, you need membranes which are very unique, which can handle high temperature, high concentrations, high pH. So that's what we kind of do. But once you've kind of treated this water and you have the minimal waste, you can take it to thermal equipment, which are primarily in terms of evaporator and crystallizers, and this gets converted to salt. So you kind of achieve the recycle and reuse and reduction, but you can also recover salts. And as Eric was kind of alluding in the morning, is that if you have designed your MLD in the right way, you can have OPEX and CAPEX benefit because the downstream thermal equipment can be reduced, right, in terms of the sizing, the energy consumption. So there's an inherent life cycle cost and value when you consider MLD and CLD. So that's what I was saying: recycle, reuse, reduce, but also recover. Let's just kind of look at some of the examples, which I like to call path to sustainability. And the first country we're going to visit is Singapore. I think people have been speaking about Singapore. Randy, you kind of touched upon it, other than the weather part. But this kind of just defines what the treatment scheme looks like. And just starting off with the issue of the problem statement, right? Singapore, as anyone may know, has got very few natural water sources. Most of the time, they're kind of resorting to getting water from Malaysia, which is the neighbor. But that does not always happen because every country is now facing an increasing amount of scarcity. So the past supplies have been from Malaysia, but they knew that this is not sustainable. So what they did was that they kind of focused on a motto which said reclaim, recycle, and reuse. And they went into an initiative which is very profound now, can be found all over Singapore, different plants. But they invested into what we call integrated membrane solutions. So it's like a cradle to grave where you kind of take wastewater and treat it into ultra clean drinking water. And right now they're kind of treating around about 210 million gallons per day, which is around about 800 million liters per day. The impact was that this reused water can now meet 40% of Singapore's water demand, which is a great achievement. But they're trying to take a step forward where they will be able to meet 55% of the nation's water requirement by the year 2060. So this is what Singapore is doing. Something closer to home, Orange County Water District, where majority of the Orange County water supply was and is from a groundwater basin, and natural recharge was not adequate because of the water scarcity again, and could no longer offset groundwater extraction. And this was kind of a problem that they have been facing for a long time. So what they did was that they kind of invested and focused on an initiative that we call the Groundwater Replenishment System, GRWS in short. And what it does that it kind of reclaims wastewater, the complete range of wastewater from Orange County by treating it with detailed integrated membrane solutions. And you can kind of look at the different process, but I'm not going to speak more about it. But it then takes the treated water and re-injects it into groundwater basin to recharge for indirect potable use. And this, at this point of time, produces up to 100 million gallons of high quality water every day, which kind of meets the demand of 850,000 residents. And this is going up by 30 million gallons in the next 6 months. And what it does that it kind of replenishes the groundwater basin, which is a good thing to do, and also protects the basin from seawater intrusion, having the proximity to the seawater, right? So it kind of achieves both the targets. And it does this at half the cost of seawater desalination. So I think there was a question in the morning, isn't it cheaper? It definitely is cheaper, but obviously you need to be cognizant of the demographics in which you live. There are countries which are blessed with the coastal Rhine. I mean, they can kind of resort to desalination, but all the regions which are landlocked may need to kind of look at wastewater treatment for their water treatment. And something much closer, San Diego County, and the picture there you see is Oceanside. And most of the Oceanside's water at this point of time was imported, and rising cost due to the water scarcity, they had to have more water, but that was kind of leading to rising cost. And the natural underground aquifer, which is the Mission Basin water supply, has been declining over the last few years. So what they did was, again, like all this good organization and utility bodies and the municipal corporations, they kind of focused on a project to look at this wastewater treatment. And they engaged into what we call Pure Water Oceanside Project. And the focus was to kind of impart the right treatment, but to remove bacteria, suspended solids, salt, microorganisms, and different chemicals from this reclaimed wastewater, and injecting this treated water into the Mission Basin aquifer to improve the groundwater resources. And here the impact again is that it can supply between 3 to 5 million gallons a day of high quality drinking water to the Oceanside community. And obviously with this, they are also now trying to expand into different aspects of PFAS treatment and all this stuff, but that's where they started. Finally, a slide that I like the most, and Eric kind of did a lot of justice to this in the morning. So when you speak of desalination, you kind of speak of seawater, and then it's kind of treated through a desalination system, which typically is an RO. You could have low pressure, you could have a high pressure, but most of the time a seawater membrane, which kind of takes care of the seawater, and you have what you call permeate water, which is filtered water or good water. And then you also have what we call the reject, and it's also called brine in many cases. And if you look at the recovery, it's kind of very limited because of the TDS of the water and the pressure requirement, which all comes from the osmotic limitations of water that you're dealing with. But you can kind of look at 50% recovery. But now, with the advancements that we've been making in the field of membranes, you are able to take the same seawater, have a specialty pretreatment in terms of nanofiltration, followed by what we call, again, specialty membranes. And this can kind of lead to what we call fresh water, but it would also help you kind of derive the salts, what we were speaking of brine mining, from the same seawater. And when you speak of the nanofiltration, again, with what Eric was speaking of, that's the first step. So what you do there, you take the seawater, and first you start mining it for calcium and magnesium, because the nanofiltration would very effectively reject your bivalents, and you can have your calcium and magnesium, which can be used in different applications, including human health, pharma, bakeries, and all the stuff. And then the brine can kind of flow through different systems, which could include a seawater and an ultra-high pressure RO membrane, which works at 1800 psi. But we are just launching a product which can also be now used at the downstream of the ultra-high pressure RO, which is probably at a TDS of 120,000 ppm or 12%, and take it from 12% to 20 or 22%. So you're talking of a water with 220,000 ppm of salt, and this could be fed directly into either a chloralkali plant or can be mined for different minerals. So conventional desalination have low freshwater recovery yield. That's what we discussed. The brine discharge raises the salinity of the seawater, and that's what's predominantly done. When you look at the Carlsbad plant, which came into San Diego, Randy, I think that was the concern. The second plant, I do not know when it's starting, but the Huntington Beach. But that has been the concern for all these communities close to the coast. And as I spoke of, new innovations in terms of specialty NF, ultra-high pressure RO membranes, and what we like to call the brine concentration membrane, because this kind of takes care of your highest solids, which are to the tune of 12%, and take it to 22%, and can help you with the 3 water sources that we spoke of. And it also allows further increase in water recovery, so you can reach higher recovery of 65 to 70%. And the impact is obviously when you can kind of start planning for desalination plant, your IRR or internal rate of return is definitely much more on the lucrative side. It also helps in the reduction of waste discharge, reducing salinity, which goes back to the ocean. But very important, waste to profits. It kind of helps you mine high value salts and minerals, which can be used in different aspects of life. So this is my concluding slide, and Joe Kaeser, who was the ex-CEO of Siemens, kind of articulated this very well, that sustainability is not just about adopting the latest energy efficient technologies or turning to renewable sources of power, but sustainability is the responsibility of every individual, every day. It's about changing our behavior and mindset to reduce power and water consumption, thereby helping to control emission and pollution levels. That's all from my side, and just would like to thank all of you for your patience.
Thank you, Jayesh. And you can see that a number of our speakers and presenters are expounding on similar themes and trends that are going on in the desalination industry. And I think that's really the case. And it is also new. Many of these things that we're talking about are being done on a limited basis now. I've done it all, and many of them are just being considered, but they do hold a tremendous potential to improve and optimize the use of desalination. Our next speaker is Dr. Arian Edalat, who is the founder and president of Pacific Water Solutions. Pacific Water, on their website, they talk about providing healthy water to residential and commercial customers, developing a complete line of reverse osmosis and other water technologies to remove unhealthy impurities from water. Arian?
Hi, everyone. Sorry, can you hear me? Yeah, okay. So, Pacific Water Solution is, as I like to look at it, it's a company that we formed about 4 years ago, and we've always been on the lookout for technologies that can bring about some kind of a change into the desalination and water treatment, advanced water treatment market. And one of these technologies that we've, over the past couple of years, we've been working on developing has been what we call active membranes, essentially. And active membrane, continuing on the theme of fouling resistance and scaling resistance, is a membrane technology that utilizes a unique phenomena from turning a passive membrane separation process into an active membrane separation process. I'll explain how that's going to take place. Now, about a couple of months ago, I was invited to speak at a very big desalination conference in Riyadh, Saudi Arabia. It was held by a Saudi government agency called Saline Water Conversion Corporation. For those of you who haven't heard that name, it's about 20% of, they own about 20% of world seawater desalination installations in Saudi Arabia, both on the Persian Gulf as well as the Red Sea coast. And they're fascinated with a couple of things. And this conference was very interested because whoever they invited, they asked one question and said, look, whatever you want to present, you have to answer the question. How can we make a gigantic desalination plant such as that? And this one is on the coast of Oman Sea, one of the world's largest installations in Fujairah, United Arab Emirates. And they said, well, how can we minimize the cost of this process? Because the cost of it is killing us. And what should we look at? What components and aspects of desalination should we look at and concentrate on? And everybody had to provide an answer to that. There were about 100 global speakers. And what I always wanted to look at as somebody who's operated these desalination plants for the past number of years, and if any of you have been anywhere near operating a plant, it's about the cost centers are about key components of the plant. In terms of seawater desalination, about 12.5% of that plant cost is intake and outfall. About 9%, a little over 9% is pretreatment. Membranes, pressure vessels, high grade alloys, a staggering 14.4%. Installation, design, all of that is 12.8%. Construction cost is about 21%. Equipment, ERDs, pumps, 25%, control 5%, so on and so forth. And operating cost, you're talking about power, chemicals, and labor and maintenance. And lastly but not least, environmental monitoring, other indirect costs of operating a plant. But what do all of these have in common? The key driver is that you have at the heart of this plant is something called a membrane. This membrane, everything around this plant has been designed to be able to give this membrane best shot of operating at the highest recovery and a more sustainable way and keep the plant up and running with minimized preventive maintenance. That's the whole purpose of every component of this plant. Everything that adds as a cost center to this plant about building it and operating it is designed around making that membrane having the best shot of survival in the longest run as much as possible, while operating at the highest possible recovery. And then that has been done throughout most of these processes, especially in the desalination sector, by the nature of this membrane, which is a passive membrane separation. And what do you mean by that? You all know this. I mean, I don't have to go through this process, but anyway, a membrane is typically in a spiral wound form factor. You get feed water coming from one side, you get the permeate and concentrate going on from the other side. And by permeate here, we mean the water that has been desalinated, and concentrate is a concentrated form of the feed, which the relationship between the volume of that feed and that permeate is called the recovery of a membrane, typically at any range. So, and any of these channels in here, you have the membrane flat sheet, you have the feed spacers, and you have the water going through it. The permeate comes at the other side of the membrane flat sheet, and the concentrate goes at the other side. This water comes with all sorts of minerals and colloids and whatnot, and if the pretreatment is not done, or even if the pretreatment is done, over time you'll have a couple of phenomena forming. One is the accumulation of these minerals at the end side of the membrane, which is called the scaling, and you have the other components such as the colloids and the biofilms and whatnot, typically on the front side of the membrane, and we call that fouling. And to control these two phenomena, which is essentially at the end of every desalination operation process, you have to limit your recovery. You have to do your pretreatment. The extent of that pretreatment depends on how badly of these minerals and colloids and biofilms and whatnot are existing in that plant. And all of that adds to the footprint and operating complexity and the cost of building and operating these desalination plants. The technology that we've been developing looks at it a little bit differently. We've done a couple of things to understand the spiral wound membrane. We made the flat sheet electrically conducting, and we have optimized the feeder spacer so we can basically apply typically a low potential. It could be an alternative current or a direct current depending on the situation, and turning the membrane into an active electrolysis unit. And by reversing that polarity, what we typically do is to make sure that all of these minerals that are charged and some of these other foulants that are either organics or biofilms or whatnot that are either partially charged or somewhat charged, to start an electrophoretic motion inside the membrane channel, and instead of residing on the surface of the membrane, go outside with a concentrated stream. That's in its most simplest form. And what that does is that it creates an inherent anti-scaling and anti-fouling property. Will the membrane still fail or foul or scale? Maybe at some point, but the key point here is that it can operate them at a higher recovery with minimized pretreatment. And overall, if you look at the scheme of things, if you go back to the front and look at that big plan, minimize the footprint and operating complexity of that plant. Because now if you have less unit operations, or if you have unit operations that are operating at a lesser intensity than they used to for a conventional passive membrane operation, that is the key, and that is the answer to that conference's question on how we can drastically reduce the cost of desalination and make it more sustainable overall. We've we've done a lot of tests on applications, but typically on a seawater, because this was prepared for a seawater application, and the main key point here, maybe seawater biofouling mitigation and whatnot, we're looking at a lot of savings because everything is interrelated. If you can operate at a higher recovery, you basically would need a smaller intake and outfall in terms of both in size as well as the amount of water that you have to pump. Less water you have to pump, less power you have to consume. Smaller the pump that you have to employ, the less, the smaller the capex of the plant would become. Same goes with the pretreatment. If you do not have to go through a cascade of softening and ion exchange and so on and so forth, it means lesser unit operations to operate, or the same amount of unit operations, but at a lesser intensity of operation and consumption. If you have a smaller plant, you have to spend less money to build that plant. The size of the pumps, the design requirements, the installation and whatnot. And if you go to the OPEX side of things, you are now looking at a much less complex plant to operate with optimized power consumptions, much less membrane replacement and chemical and waste disposal and labor and maintenance and so on and so forth. So the key at the bottom of all this thing is having a different look at the way membrane separation is happening right now, and turning it from a passive separation into an active separation, and thus being able to do some level of fouling mitigation or scaling mitigation, and that would eventually impact the entire ecosystem of process design and desalination and pretreatment and so on and so forth, very similar to what the other gentlemen were talking about. Thank you.
Thank you, Arian. Very interesting, and again, along the lines of some of the other things we've talked about, that fouling resistance and reducing fouling and the impact is a big impact on desalination systems, and a lot of work is being done in that area, and we've sort of seen that today. So let's throw it open for questions for either one of our three speakers. So if you have a question, let me know, and please state your name and affiliation. And you do need to talk into the microphone because we're recording, and so you need to talk into the microphone. Anyone? Subir?
I have a question for Jayesh.
I know he has an answer.
Hi, Jayesh.
Let me think.
One thing you mentioned about very high concentration brine treatment with RO seemed like when you mentioned that you will take it from 12% to 20% TDS.
22%, yeah.
Are you planning to do that in a cross-flow mode or dead-end mode?
It has to be a cross-flow mode because at that high TDS, you don't want to kind of be dealing with concentration polarization issues.
Yeah. So my question with that is, isn't the cost to overcome DP, which is the across the channel in that viscosity, going to be far more overwhelming than the TMP related problems? I mean, the viscosity effect is my key question about that.
That's true, but I think you're assuming that it's an RO. It's not an RO. It's a new membrane chemistry, which is more on the premise of a nanofiltration.
Okay.
So you can kind of deal. So when you speak of an ultra high pressure RO based on the osmotic requirement of the feed water, you definitely need to go to 1800 psi or 120 bar. But when we are speaking of the BCM membranes, which is the brine concentration, that goes up to 1200 psi.
Got it.
Yeah.
Thank you.
Additional questions?
With your permission, may I
Yeah,
have
sure.
a question to maybe both Arian and ZwitterCo? Again, it's very curiosity driven. Are both of your membranes based on a polymer matrix? You have a polymer matrix in your membrane. Yours would be a polymer matrix as well, or? Okay. I am coming from the battery sides of things. When you cyclically do things with polymeric materials, they have an end of life which is not dictated by fouling, etc., but by something which we call hysteresis. Has that been studied in your case, which is a chemical hysteresis, in your case, which is kind of a polymer dealing with electrical cycles and fouling cycles?
I might have to ask you to clarify what you mean by chemical hysteresis here.
Typically, these zwitterions, how many wash and foul cycles will it bear without losing their effectiveness?
So we haven't found an endpoint yet. I think what makes what we're doing with them unique is we're not just coating a membrane with an anti-fouling surface, right? The selective barrier is a self-assembled structure where that zwitterionic character is all the way through the pore channel. And so what you're really talking about is sort of the end of life of the material at that point, right? And, we've put them through accelerated life cycles, that we believe represent several years of operation, and they're stable. So we don't see an effect like that playing out.
You work in very challenging waters,
Yes.
and one of the things I have seen is the curveball that is thrown in dairy or those types of very hard biological waters is quaternary amines. Quaternary amines. These are basically molecules that are supposed to chop down bugs. So the question becomes, how would the polymeric matrix of the zwitterions survive those? It's for just the challenging waters, but it was a very interesting technology. I heard about it for the first time, but these are obvious questions that came as a chemist. Maybe for Arian.
Yeah, sure. Thank you. So as far as longevity is concerned, obviously we haven't run them for days and months on end, but so far we've run them in extreme conditions of pH and up and down and so on and so forth. We haven't seen any, and these are like a week or so and whatnot, and we haven't seen any drastic impact on degradation of the material and whatnot.
Targeted application in this case is primarily
Primarily, yes, the couple of focuses is groundwater, high mineral content, highly scaling propensity, groundwater and seawater and so on and so forth. So these are, because of the nature of the membrane, they operate at a higher TDS a lot better than they do at the lower TDS. Electricity, it's simple as that. So, and
excited about
And but as far as longevity, we don't expect any longevity issues because the material is fairly standard stuff and it's been used in other similar applications. We haven't done any longevity tests because it's early stage, but we don't expect any sort of.
And I think, Subir, just one more point. When you speak of the membrane, I think the membrane characteristic helps you. It could be a neutral charge or it could be a different charge to counter the charge of water that you have. But I think the whole success does not just only lie on the membrane chemistry. It's also the way you make your membrane element, right? Because there are different constructional aspects in terms of feed spacer, the geometry, the feed carrier, and also the ATD, right? Because at some point of time, what Arian said that whatever you do, fouling is going to happen because that's the cause, right? So if you can have an element which can kind of, delay that, that's important.
I highly agree with that the whole thing system contributes.
So I've been, for the past couple of years, an integral part of that brine management with our mutual client back in Saudi Arabia. And one of the issues that I've always been having is high temperature. Two reasons. Why is the water is at a higher temperature over there than other places. And the second thing is that by the time it passes all of these high pressure pumps and this and that, and you're looking at several stages and it gets much hotter. You're looking at 50 degrees centigrade or whatever. And that kills the performance and flux and rejection of the membrane all along. What, in your new product, I'm just curious to know, how are you mitigating for that impact?
I think what you kind of stated is that you can't go against nature, right? Because that part of the world is going to have high temperature and the water. And when it passes through the different stages, I think that's going to be an incremental effect on the temperature. But what you could also do is that other than the low fouling aspect, the ultra high pressure aspect, if you could make your membrane to withhold high temperature. And that's where we are trying to play around with, right? So if you had any membrane can work up to 40, 45 degrees C, right? But it's performance, but we are kind of working on a special membrane with the different constructional aspect, which can take temperature up to 60 degree, right? So that's where we are kind of playing around. Yeah. So low fouling, high pressure, pH, and also the high temperature.
Membrane and the feed spacer.
Correct. And the glue.
Any other questions? Okay, with that, I think we have time to take a short break, stretch your legs, do whatever you need to do, and we'll start again with panel 4 at 2:00.